Critical value z-test for the mean, Chapter 9. Example 1. In a random sample of n equal 15 patients, the mean creatine level x bar, 1.4 milligrams per deciliter. This is taken from a larger population. The population of all potential patients, creatine level is normally distributed with mean mu unknown, but with known standard deviation sigma 0.5 milligrams per deciliter. And we want to compare it to the creatine level of the general population, where the mean is 1.0 milligrams per deciliter. Now, this is a little bit unrealistic because usually, if you don't know the mean population mean, you're not going to know the population standard deviation either. However, the advantage of this example is that it kind of follows directly from the central limit theorem, and kind of illustrates the usefulness of the central limit theorem. And also, for large samples, actually it's less important to it's likely that the sample standard deviation will be the same as the population standard deviation, and it's less of an issue here. But anyway, so with 95% confidence, we want to test H naught, mu equal 1.0 milligrams per deciliter. Creatine level is the patient creatine level is the same as that of the general population, versus the alternative HA, mu not equal to 1.0 milligrams per deciliter. Patient creatine level is different from that of the general population. So this is a two-sided alternative. Our confidence level 1 minus alpha is 0.95, and our level of doubt 0.05. Okay, so step 1, we want to use the z-table in reverse to get the critical values. Our table is so we want to reject H naught if we have either extreme here. In the middle is where we don't want to reject H naught. So the 95% should be in the middle. Because our table only has the probabilities for the z-score is bigger than 0, it only has the upper half. We actually want to look up 0.95 divided by 2, which is 0.475, and look for 0.475 in the body of the z-table, and it's in row 1.9, column 6. So the upper critical value is going to be 1.96, and the lower critical value would be just the opposite, that would be negative 1.96, because the normal distribution is symmetric. And then we can compute the test statistic, x bar minus mu naught times square root of n over sigma. This is actually a z-score. I'm calling it a z, but it really is a z-score. You just have to adjust the standard deviation for the sample size. That's why there's square root of n here. But otherwise, it's the same z-score that we were working with earlier in the course. 1.4 minus 1.0, and compute that, multiply by square root of 15, divide by 0.5. It comes out to be approximately 3.10. And because our test statistic is more than our upper critical value of 1.96, we reject H naught with 95% confidence and conclude that the mean creatine level of patients is different from that of the general population. Now that was a two-sided test. If prior to collecting the data we were certain that the creatine level of patients was not less than that of the general population, we could do a right-tailed test. So we want H naught is going to be the same, mu equal 1.0, creatine level is the same as that of the general population, but the alternative, instead of a not equal to symbol, will have a greater than symbol here. The alternative HA, mu is greater than 1.0 milligrams per deciliter. Patient creatine level is higher than that of the general population. So now we're putting all of our doubt on one side, and so the number that we want to look up in the table is 0.95 divided by 0.95 minus 0.5. So we want to our table only has probability for the upper half, but we want so it's not going to have this the lower half 0.5. So it's, if you do 0.95 minus 0.5 is 0.45. Look up 4,500 in the body of the table. It's not there exactly. It's halfway between the numbers that are in row 1.6, columns 4 and 5. So we can take the average of 1.64 and 1.65 to get 1.645 for our upper critical value. The test statistic is the same as what we computed before. It's 3.10, and now it's even there's even a greater discrepancy between our test statistic and the upper critical value. So we conclude even more emphatically that the creatine level of patients is higher than that of the general population. Part C, if prior to collecting the data we were certain that the creatine level of patients was not more than that of the general population, we could do a left-tailed test. H naught is the same, mu equal 1.0 milligram per deciliter. Patient creatine level is the same as that of the general population, but now the alternative HA has a less than symbol in it. Mu is less than 1.0 milligram per deciliter. Patient creatine level is lower than that of the general population. So now we want all of our doubt to be on the left side, and so it's going to be the same critical value we had before, except we have to put a minus sign in front. It'll be negative 1.645, and our test statistic is the same at 3.10, and in order to reject H naught on the left side, our test statistic would have to be less than the critical values, but it's not. 3.10 is more than negative 1.645, so that means we fail to reject H naught. Sample does not provide enough evidence to conclude that the mean creatine level of patients is lower than that of the general population. And in order to use this procedure, we need to assume that the population standard deviation is known, and that either n is at least 30 or the variable is normal. And that concludes this presentation.